manifold looks like, and you can try to perform analog handlings in this thing, and you will, for instance, can do something like this. You don't have to do it like this, I suppose, but it's one way you can think about it. And the way, I mean, I want to present it like this because I want to convince you today that these, I mean, having these handles at your disposal and sort of moving them around in a geometric way will lead to an algebraic element at some point, which is related to it. And it's really the way it's constructed. It comes from manipulating these handles in the geometry of the manifold. Okay. Right. So that's sort of all about closed manifolds. If you just have a closed manifold, you can start building it from scratch by having a zero handle like this disk, and then attaching other things. And there's a relative of this function for the relative case, which says that if you have a coordinate, say going from M0 to M1, coordinate like this, then there is the relative quantity. So telling you how to attach handles to M, from 0 to 100 of all the quantity. So you take one side, and then you start attaching handles to that. So informally, I want to write this as, well, that your coordinate W looks like you start with M, and for some reason you cross the interval on the cylinder. But that's most likely not the coordinate you're looking at unless W is already in the cylinder. So now you have to attach things to that. So what you then say is you attach some handle 1 or some dimension. You have a finite amount of handles that you add to build all of the coordinates. Just these are the handles. And then again, as in this case of a surface where there's only one handles, because they've already done everything. Of course, here these have different dimensions. So the typical handle will be something like dk times n minus k. In this case, it will be equal to 100 dimensions. So in any case, there is some way of combinatorially, in some sense, constructing your coordinate from one side by attaching these handles. And then again, well, you can imagine if I just wiggle my attaching a bit, it will not change the coordinates. Right? So the point is that there is going to be handle moves that are allowed, which change your particular presentation as such, but will not change the diffeomorphism of your coordinates. And the point is that you can try to sort of do a from algebra to topology concept. There's a principle maybe, so algebra topology in a certain sense. So for instance, say we're in a simply connected case, say n equal to power w 0, just for ease of representation, and assume that the relative homology of 0 and w is 0. Okay, so that there's no relative homology. So for instance, you could say that maybe that's a better way to say that this is usually the homology. So such homologies can go into the world. So assuming you have a coordinate where the endpoint inclusion is a homology equivalence, there is no relative homology, and then there is going to be an argument in these handles like techniques that tell you you can arrange a relative handle decomposition with only k and k plus 1 handles for so you can pick some number which is suitably outside of 0 and the dimension of the coordinate, and then the statement is that you can find a handle decomposition where you only have handles into adjacent things. And now you can, okay, so that's sort of taking information that some homology is not dimensions, so we manipulate these handles to get some. Now, from here we can play the game back again and try to use this handle decomposition to calculate the relative. So, the relative handle chain complex will look like we have a couple of zeros. So the idea is that it will only consist of 3 modules, and according to how many k handles we have. So there will only be k and k plus 1 handles. So the chain complex will be something like, I guess, one and two. Will only be in 2 adjacent degrees, but there is no homology. So that just means that the differential here is because there's no homology. And the main idea is that you incorporate incorporating pi1 correctly, so all these fundamental groups, well, then you will just work with the universal cover and keep the pi1 action into account all the time. So what you will find is that P is an invertible operator on the finite damage, the finitely generated free Z pi. So that's taking the pi1 action into account, means that this is going to be 3 modules over the grouping. And because it's an isomorphism, there's going to be some invertible operator. And then the point is that this is going to determine a class inside the following thing. So you can just, this is going to be, okay, let's just say like this. So you can look at all invertible matrices over the pi, just make the union of all those for their genus unity C pi. And that you can abelianize in the Abelian group, and your element will give you, your operator gives an element. Now, this element is not going to be quite well defined, mainly because of the choice of how you write this as a fused pi. Okay, so you have to divide something out. Maybe the subject which is generated by plus minus just the units of C pi sitting inside here is just the 1 by 1 matrices. So these you have to divide out in order to get a relevant element, and it just turns out that this is the algebraic group of pi, the first one. So in the beginning I told you, algebraic K theory is built out of modules and your isomorphic. Using isomorphic is the element here. And then, okay, you have to divide something out, and this quotient is usually denoted as the y group. Okay, so from this description we obtain an element in this y-tech group, and now it's a sort of, okay, one can try to find out when is this element. Maybe I should also call this the torsion of W. So let's call the y-tech torsion of W, this element. And so this torsion is going to be 0 if and only if you can perform elementary row and column operations to estimate these identities. Now, these elementary row and column operations can be sort of mimicked on a geometric level. So in other words, you can rearrange your handles with the handle slides to make your differential be induced be having these one-on-ones everywhere. This will say that each handle has a corresponding k plus 1 handle, the one with where the entry is 1 that means. And these two are the only ones that intersect. All other ones are sort of destroyed from each other. And they intersect transversely at exactly 1 point. And then it's again a geometric argument, and those you can just cancel. Then you can take both of them and delete them, and you will not change the path. So this group being 0 implies that W is isomorphic relative to M0 to be trivial. Because at the end of the day, removed all handles, you have to attach to the field from M0 times I, and then it's just times I. So the main point is that this implies that M1 is diffeomorphic from 0. Because we can look at the other end of this diffeomorphism, run through this diffeomorphism, and look at the diffeomorphism. This might be a complicated diffeomorphism, and the fact that this might be complicated, or that is a complicated diffeomorphism, is the source for the Poincare conjecture performed topologically, and the two homotopy spheres are homomorphic to a standard sphere, but not different. because some of that, yeah, one creates a complicated diffeomorphism that you cannot generate sort of smoothly. Okay, so this whole construction is a theorem known as the Escobar theorem. Okay. So the Escobar theorem says that you can look at H coordinates over N, by which I mean a W and N and blah, blah, blah. And you divide out the relation of diffeomorphism of such relative to N. Okay, so you look at diffeomorphism class of H coordinates over N, which are the identity of N. And to such things, by all these Handel manipulations, we can associate a portion in the white group. And okay, the actual theorem, so what I explained is that if this element goes to 0, then I've tried to indicate why this coordinate is trivial and the same is effects. So that's the H coordinate theorem, telling us about the set of isomorphism classes of H coordinates over N. So that's good. I mean, it's interesting, but in the spirit of the center and of many talks that were around, let's not only consider this set of isomorphism classes. So let's instead consider the moduli space of all H coordinates. So we're trying to upgrade this to a better statement than the bijection. Better version. A better version would be is to consider the moduli space H of M of H coordinates. Now we can think that a point in this moduli space will be just an H coordinate, and then where the path from one to the other is going to be a family of H coordinates over a simplex and so on. So you can build a sufficient space out of that. So there is a nice space of such H coordinates, and maybe we would rather like to understand the whole homotopy type of space and not only this is the left hand side. So it's really made as the left hand of the right hand side. Okay. And I mean, this space is interesting for at least 2 reasons. On the one hand side, it's sort of the classifying space for bundles of H coordinates. And it could well be that we have a manifold, all of which H coordinates are trivial, but bundles might not be trivial. Right? So this is going to be captured by the homotopy type of space. Without an interesting panel of H coordinates space. But on the other hand, it also turns out that just as a side remark, the group space of this space of H coordinates is space of concordances. So those are essentially diffeomorphisms from n times I, n times I, fixing some part of the boundary. So most likely get confused with the probably diffeomorphisms that are done the identity of the function. So it's sort of a flabby version of actually diffeomorphisms. And okay, so the space is also interesting. I'm just trying to understand what are diffeomorphisms or families of diffeomorphisms. Okay, so that's an interesting space. And this equivalence, this bijection, you can wonder whether or not this might be upgraded to a statement which tries to compute this space in terms of algebraic entropy. Let's be bold and hope that something like this will be true, because this is something that is and the statement is that, as far as I know, this is not true or known or anything or expected, but so you can do the following stabilization. So there's going to be a map from the space of H coordinates to n over n times n1. You just take an H coordinate and cross it. So remain H coordinate. And so there's all these stabilization maps. This is supposed to have lost information about M because yeah, you didn't really care anymore about the particular average, only cared about what remains after crossing between this crossing. But it turns out this stable H cobordism space is in fact, you can describe that as a behavior. I should. So there is one important ingredient. This is a saying that the map from A to N in the stable H cobordism space is an iso on homology group for one line roughly lower dimensional. Can be better for particular n, but that's roughly what holds. And there's also a little epsilon down in the beginning. So if your manifold is too low dimensional, then it's for high dimensional manifolds, the statement is that the homology groups of this space, at least in the range, will be controlled. And okay, so this is also, this number is where this where this number was. Notice that 2n is roughly 2n. So this is something that's there, and then you can try to you can try to wonder whether or not this stable H cobordism space can be described in terms of algebraic K theory, and there the answer is it's a term of called the stable parameterized cobordism term. Divide all the unknowns. So with the history that I believe Hatcher announced the proof of it, which was not quite correct. Weithausen reimagined how one should prove this, and then Weithausen and Wortmus finally actually finished a proper proof. And it says that there is an equivalence between this space of stable H cobordisms and construction purely intrinsic to stable homology theory and algebraic K. So I think that there is a map, and I'm trying to explain some of the stuff. Okay, so I've already indicated that there is a gadget like this spherical group ring over loops M. It's some sort of ring in a generalized sense in homology theory, of which it still makes perfect sense to take K theory. And it turns out that okay, so this is, I mean, in the technical sense, this is a spectrum or as an underlying space, and you have to take a manifold, view it as a spectrum, and then there's a canonical comparison map called the unit map or the assembly map or something, and then you can take the fiber of this map. And the statement is that there is an equivalence from this stable H cobordism space to something that is purely described in terms of K theory. And now you observe the following diagrams. We have your space of H cobordisms, sort of geometrically, I say this is interesting to do. And you can pass it with stabilized version. I want to stress that this loses information. This loses info, but only for I in a low range of degrees, it does not lose. Now here there is this equivalence to a fiber of such a K theory space, which it sounds very complicated, and in particular I haven't said anything of why any of that should relate to this K group of C pi that we saw earlier. It's just some complicated homology theoretic gadget. But what you can do is you can use this the map by saying that there is a map from the spherical group ring just to this ordinary ring, which you, I don't know, you can, there's a world where you can view both on equal footing, and in this world there is a canonical map which induces something on K theory. So we also get something on this map from K theory. And now well, this composite gives you a map from this space of H cobordisms to the fiber of the map from sigma plus M to the K theory of C pi. Just the ordinary K theory of C pi. And it's an exercise to calculate that this pi 0. So that's the exercise we performed. And now there's sort of one thing that we need to understand in order to say that whatever I've tried to tell you is a stable parameterized H-cobordism term has anything to do with what we call the S-cobordism, the establishing structure bijection. And the instance that goes into this is the following. So this is this key property of K theory I wanted to address. So key property of K theory is that, okay, so the name is this map. Okay, so how do we do this? This is what's technically called a ring spectrum. So it has a lot of higher homotopy groups potentially, and it has one zero homotopy group. And the claim is that this map is an isomorphism on pi zero, which just means where this space, I mean, it's a discrete thing, it only has one homotopy group, namely Z pi, sitting in zero. And this just is a canonical map from the ring spectrum to pi zero. So the statement is they have the same pi zero, but this term is much, much more complicated. And the key property of K theory is that after applying K theory, it's an isomorphism on pi zero and pi one. Okay, so technically speaking, for those of you who know about ring spectra or spectra in general, the statement is if you would replace this by an arbitrary map of connected ring spectra, which is an isomorphism on pi zero and also an isomorphism on higher homotopy groups in up to a given range, then K theory will add one to that range. It will be an isomorphism up including a bit more. Okay, so that's the property K theory has, which allows to calculate, of course, then you will find that this map is okay. So this is what comes out of this discussion. In other words, this equivalence between the stable H, this space of stable H cobordisms, and this K-theoretic gadget is really sort of a lift to a space value version of this bijection that we found on the level of sets. And now the point is that one can use these kinds of ideas. I can leverage these ideas to compute and say in range things like rational homotopy groups of, if you want to put this and rational homotopy groups of things like different of say dense spaces, or things that spherical space forms, and then I don't know, things that whose universal cover is a sphere, also rationally, and also maybe things like star homeomorphisms of n rationally, if n perhaps contracting the universal cover, so-called spherical manifolds. And the reason that these things work rationally but not integrally with what I proposed, or with these ideas that go into such constructions, has to do with the following fact. Let's do that following operate. It has to do with the fact that the sphere spectrum, this guy, if you rationalize it, it becomes that. So that's a property of, I don't know, it's a statement that the stable homotopy groups of spheres are all finite, except in pi zero where it's zero. Okay, so that is something that you can leverage to say that this map, if this map were a rational equivalence, then there is an upgrade of this kind of version telling you that also the map on K theory is a rational equivalence. So K theory is sort of very sensitive to the other map, which is a finite isomorphism, and it's an equivalence to the eyes of, I don't know, inverting P localizing, P adequately or rationalizing or something. It remains so after applying K theory. So you can leverage these kinds of arguments and hence get results about rational things from this point of view. Unfortunately, the sphere, if you want to localize the sphere at anything to become like Z or something, a localization of Z, you actually have to invert all primes because it has torsion for all primes in theory. So this kind of gadget will not, this principle will not help you with anything better than rational calculations in principle. So this is the property of K theory. But I want to tell you that there is different instances or you can make use of such invariant properties of K-field that I'm going to explain now the rest of the talk. I want to say a couple of things that one can do to manipulate K-theory in the hope to obtain some communication. And I think the applications of what I will present now are sort of orthogonal to the motivation, but nevertheless, this is one way that at least in these rational calculations, K-theory enters into the geometry of Manifolds. Okay, so slightly different question is, how do we calculate K-theory? If you have a particular ring in mind or a particular ring spectrum like sphere or something, I mean, how do you actually take it? And there are, of course, many things you can try to do. One prominent thing is so-called trace methods. Trace methods say something like there is a map from the K-theory of a ring to a gadget that could really constructed. There is a kind of Chern characters, or there's a cyclotomic trace. And it turns out from the theorem of Goodwillies and Dundas-Goodwillie-McCarthy that this gadget COR, whatever it is, it's sort of supposed to be more accessible to explicit calculations, but at the same time a very close approximation. So you can try to use such maps, calculate on the TC side, and deduce things about the K-theory side. And this was massively implemented by a lot of the hard work of Pete Munson's last people in that area. And there is many things nowadays known about these kind of trace maps, including there's a very beautiful result about the fire of the cyclotomic trace map, and also due to Dustin and Akil and Metzinau about invariance with respect to the quotient and everything. So there's a lot of things one knows about the relation between K-theory and, say, this homology, cyclic homology term. And if you're interested in rational K-theory, this easier or more classical invariant. Okay, so this is in principle saying that once you try to calculate something, you try to calculate TC. The second thing you can try to do is just general descent property. Well, that just means something like open cutoffs, or maybe image cutoffs or something. There are many types of topologies on schemes or rings you could imagine, where you say maybe I can pick my ring apart into smaller pieces. I know everything on the smaller pieces. I put it back together. So those would be descent properties of this kind. And one general thing you can ask in sort of commutative algebra or in algebraic geometry would be the question of the pi descent, which in general does not hold. If it does not satisfy this, it makes it more complicated to compute. But also by now there is a quite good understanding about sort of the failure of its pi descent. And again, Dustin very made very contributions in that area. There's a lot of things in this direction one knows by now. And a third property which is used for calculations is excision. So excision is more of a purely ring theoretic flavor, and it's more about, say, more about force color. So let me do an example of what an excision property would be. And let me do an example which comes back to these two breaks that we had. At the end of the day, we try to calculate some explicit thing. So, for instance, you can do the following. So, if you let G be a finite group. For instance, you could imagine that G is the combination group of an n space. So, the manifold takes pi1, suppose it's finite. And the typical situation of excision is as follows: is that you have a map of rings, and in this case, I want to take the map into something I write n, which signifies QG, and this is the maximum form. So that is just a lattice inside QG containing the G end of maximum rank. So these things exist and are, from a ring theoretic point of view, much better behaving than CG. By the way, for instance, if you take the sigma here, then this maximum order will just be Z times the sigmotomic extension. So you add up the square root, like a P square root to Z. So it better behave than the And so the general question we have with excision is that you find an ideal inside CG, which is mapped isomorphically to an ideal, and then you divide out on both sides and look at a particular split. So the ideal you can consider is I being the one that's generated by the number of elements of G inside M. Right? And you get one that's generated by that. And it turns out that this idea is called the conductor inside CG is not generated by the number of elements, but it is the lies. And so in particular, you will obtain the square of this time. And okay, there's a general principle telling you this is a full-deck square. And so one question is, if I take the square, is this a full-deck? And okay, being a full-deck essentially just means, so either you know what it means, then it's fine. Or if not, it just means that suppose you know 3 of the 4 corners, the K series of 3 of the 4 corners, and then you will be more or less able to also pick it up. In principle, it says that you can calculate the fourth term of the other. Okay, so that's a question you can ask. And the answer is going to be no. Unfortunately, K3 does not satisfy this. But what I want to tell you is that there is a formula for K3. Write down sort of how much it does not satisfy excision. So let me formulate a theorem which is now sort of a general situation, and then we can try to apply such methods to particular excision examples. Maybe I should also write down one other example that illustrates a bit better this idea of closed covers. Another example, take a ring K, and then you can look at something like how the number ring is variables and divide out the product of the rings. And then okay, this is going to be a full deck of rings, and you think about this as the ring of functions on the union of whatever this is the ring of functions on, and this is the ring of functions. So this sort of means this is an affine line, it's just the functions on the line. The other one is also the functions on the line, and so this is going to be the problem system. Simple thing that you cover by these 2 coordinate axes. It's a closed cover, and you would like to know, can you calculate the K theory of this curve in terms of over 3 terms? And again, the answer is no, you cannot, but you can try to understand what is the failure. When we give a formula for the failure. And okay, so the general term one can prove in this direction. Is the following. So we can just generalize the situation a bit and first consider an arbitrary square, so a full deck square of rings, like that. But you are absolutely free to think that all rings are just ordinary rings. And then it would be good. So in all of these situations, from here to observe that some logical map is surjective. So probably best to think if you think in the discrete case, just think of a case where you have a surjection like this. And this will be exactly the case if you have a map from A to A prime, which sends them up to isomorphic. The other idea, and then you just take the portion. So that's sort of the general situation you look at. And then the claim is that, well, then there exists a new ring, which will get some formula, and I'm going to abbreviate it like with circle dot. So it's not like this, but let me just write a little circle dot for it, and the diagram, which is of the following shape. You still have your good old big diagram remaining, but then you insert this little circle dot inside. Okay, so this is now the diagram hash code same. And the statement is such that this hashtag diagram is. So, in other words, this really just means that this implies that if you wanted to know whether or not K theory applied to the original diagram is a full vector, or whether or not you can calculate, say, the K theory of this guy in terms of that diagram, this one. Well, our theorem tells you you can calculate it in terms of this, and this one. Well, so, in other words, it happens that this guy is a full vector if you only have from circle to the pilot. Okay, I mean, this is maybe for the moment it sounds a bit, I mean, how useful is it? And I think it's very useful because it tells you that the question of whether or not this diagram is a full vector, sort of it has an answer, so to say, before a line. So for instance, if you can show that this map is an equivalence of rings, then obviously K theory will be an equivalence. And you don't have to prove anything complicated about K theory. You prove something before applying it, and then it defines. And this kind of idea that you have a formula for the failure of excision before applying K theory can be leveraged to reprove a couple of things that have been known previously, and sort of just from my point of view, capture or like organizes a couple of the arguments. So some consequences. Oh, yes.
You have a reversal properties.
No. It's a construction, and the construction is also no. So in general, it is hopeless to think that this ring will be uniquely determined. I think, or maybe. But no, it's not giving in terms of universal property on the level of rings. In fact, the way one proves this is to pass everywhere to categories of modules. To prove a statement about, so that you find the category of modules that sits here, and then you prove that it comes from, it is the module of a ring. But I'm not aware of an a priori universal property. But at the very end, if I'm allowed, in some situations, it does have a particular universal property. I can tell you how. But in general, this is quite mysterious. But what I want to say is that although it's quite mysterious, it has some formal properties that don't allow you to exactly say what actually this ring is, but which suffice to prove the following consequences. So for instance, if you can, so suppose this ring, this is all this ring is. Now in this example, these kind of squares, they are called Milnor squares. So if you're in this situation, and you happen to know that the form for A prime and B over A, right? A prime and B are modules over A. You happen to know that this would carry for say the range 1 lesser equal I lesser equals to n, then you will prove that this map is which has to do with the fact that we can just calculate the homotopy groups of this ring. They are just given by these 4 groups. abstractly. So if they vanish, it tells us that the map from here to here is an isomorphism or many homomorphisms because all of then these kind of things you can use. And the consequence that you obtain is that you sort of have a long sequence of Miami-Torres type in K-theory relating this, and this in a range. Right? Because in general you have it if you include the circular ring, but in this little range you have an isomorphism to this one. And so this consequence was the effect that this decision theorem. So this can get a very intricate argument using group homology arguments to prove something about what kind of squares still give rise, at least in the range, to these biologies. And you can sort of reprove it by the mere existence of the circular ring plus this property that you can describe the form of properties like this to obtain a result along these lines. And there are many variants that you can now use, all of which build on the fact that we can control the quality of this map through the eyes of K. Always by saying it induces an isomorphism in forms of homology groups, or it induces an isomorphism rationally, or after P completion, or these kind of things. All these properties persist after the map. So these are the general methods that you can use to apply. So for instance, you could try to apply such a result to that square, and it will tell you at least that this square is going to be rational. So if you're only interested in calculating rational K-theory CG, then it will turn out you might as well calculate the rational K-theory of N, which is a firm of Borel's that's also sort of well known. But nevertheless, you can try to play these kinds of games on the K-theory side. So I will finish with saying that, okay, so currently a lot of my work, partially, of course, revolves around understanding the circular. It's a bit intricate in general, but I hope that we can sort of give formulas for it in particular instances and actually also use it at some point, coming back to step one, using trait methods to actually calculate things about K-groups in particular examples once we actually give the formulas. In some cases we have. So that's one of the portions I think about, but I deliberately wanted to tell you about the relation of manifolds, of which this is a bit unrelated, to also let you know that I also like geometry, manifolds, and things related to coordinates and categories, things Oscar is going to explain about. So if you're ever interested in chatting or just doing that along these lines, then I'd be happy to do so. And so thanks for your attention.
You know what the circular is if this K2 is it? Like T is signaling about P, isn't it?
Yes, I think so. So I think, but okay, so there's a formula and then you're still going to say it. But I think if, say, let me do this guy, then I'm not going to work with this square. I'm going to take a different square. And I think you can, if I understand correctly, you can go to the sigmotomic extension, and you can go to Z, and then this is going to be full over. And I believe that. So this comes back to Fabian's question. So there's a general principle. So of course the polynomial ring maps it, and also maps here and here. And you can observe that Fp is the tensor product with this guy, and that. That is going to be. I mean, unless I thought about this morning, I hope this is correct. But on this, so I think this is true. So it will turn out that you can write this lower term in terms of a relative tensor product of the outer terms along something which sits beneath the guy we start with. Whenever you're in such a situation, then the conclusion is going to be, so that's something that I'm currently trying to write up with scale, is that the circular ring is going to be a push out of E1 ring spectrum. And then it's going to be with this. So if the Z push out of E over T, the Z. And I need to write this as okay, and sort of in a homotopy theoretic sense, you set T So they generate some P from the affiliation to one. Right. Almost like a P. I think that is sort of the formula to get out in this. In general, these rings, these circular rings in situations of that kind will be sort of really type of so for instance, in the case of the circular, this case, the circular ring will be just polynomial ring is a variable to be 2. So yeah, typically in a lot of examples we'll find such three kind of algebras of three dividing out certain relations in the E1 world. And of course, I mean, calculating the K theory of this, I guess, is don't have a clue. But of such things is I suppose, much more trivial. So that's one of the things that we can work out in the future. Yeah. But okay, yes. Yes.
So you mentioned P is not dividing across for the ring at the beginning, the number purification.
Yes.
Studies. It's a hard statement. So what happens now? Can you characterize the property that P squared is not dividing across?
I have yes, I have no clue. Doesn't you? I have no clue. I don't know.
There is some expression. But then you have to look very closely to see what it is. I mean, everything you can express in terms of your solid theory, you can also read off of here in some way or another. But you have to look to see what it is. It wouldn't be as simple as something like that. You might even need to look at others to come in their case in principle.
So you said this circular thingy is defined in terms of a category first. So what is that?
The category?
Yeah.
Yes, that's actually quite easy. So what you do is from this original diagram, you can look at something like just the perfectly right category. Yes, homology theory of chain complexes up to quasi isomorphism. Fine. And now, okay, so the statement is going to be that you can like this. So what you can construct is a category that we write as P. So that's a category which consists of an object in the derived category of A prime, an object in the derived category of B, and a map from the base change of X over A prime with P prime to Y. Not an isomorphism, but just a map. And okay, so this you can look at. And it turns out that, okay, this kind of you can think about as like sort of like a bundle of BP categories over BPA. Right? It's not a product, but it kind of. Yeah. So okay, this is not a product category because there's this morphism there, but through the eyes of K theory, it looks like a product. You can forget the morphism. So K theory of that category is just the product of this one with that one. And now what you show the fact that the diagram that we started out with is a pullback tells you that there's a prefixation distribution of categories like this, and you can just pass through the quotient of categories. So that's something that now that we have this language of higher category theory around makes sense. It's just on Medier quotient, not on the level of triangulated, but on the level of stable infinity categories. And then you see that this category is generated by A prime, this one is generated by B. In this category, you have two generators, one coming from here, one coming from there. But in this quotient, you've identified both. So this category is going to be generated by a single object, and then it's a content of this theorem of Schrader and Shipley that single object, its endomorphisms have the module category precisely Q. So this is going to be the category of modules of the derived category by the Schrader Shipley theorem. And then I mean, that's all sort of trivial. The only thing that you then have to work out, which is also not very complicated, is to calculate the homotopy groups of this string and to calculate sort of at least the underlying maps of spectra that are around. You don't have to describe what, I mean, just the formalism gives you that this is a diagram of rings, and the map of rings, you know, is as, it uses an isomorphism on homotopy groups if and only if you forget that it was a map of rings, and it does induce an isomorphism. So in order to calculate the quality of this map in terms of the homotopy groups, you don't have to know about the ring structure and everything underlying. You can just calculate fully from